between you and lunch, so I'm going to try to go at a decent clip. But yeah, my name is Tamas. I'm a fifth-year PhD student now in the Weiner Lab at UCSF. And before I get started, I just want to let everyone know that this presentation is available at this address URL because this is a Jupyter notebook that you can actually run all the cells in if you want to play around with this later. I also have this URL at the end if you don't want to write it down now. But thank you to the organizers for letting me talk about working with multidimensional microscopy images in Julia. So just a little bit before I jump into that, I wanted to describe a little bit about what we do as a lab. So the Weiner Lab, we work with multidimensional microscopy images with lots of metadata, like many people here. Really, in some discussions, it's like the only unifying feature of our lab, really. And so, but we're really interested in leveraging kind of cutting-edge optical methods to answer questions about cellular decision-making. And particularly, especially in my work, it's focused on cellular polarization and motility. So just to give you guys a couple examples of what this looks like, we do a lot of smart microscopy where we do optogenetics inside of single cells, and we use spatial light modulation to control like projection and activation of subcellular components inside of a cell to reorient the cell or change the decision making of the cell. We also do in vivo super resolution 3D imaging to look at motility of cells inside chick embryo here, for example. We also do rapid confocal imaging really to do single particle tracking inside of cells as well. So that's just to give you sort of the gamut of things that we do. There's a lot more. But really, our data ends up boiling down to the same kind of set of properties. A lot of times they're multi-channel images. They're often Z-stacks. Quite often we use non-uniform time sampling. And we use many different microscopes, like a lot. And most of our imaging is done via Micromanager, but this combination of properties ends up being difficult to work with. So why is it difficult? It's really it's pretty difficult to write general algorithms that perform well using current tools. We have lots of code that is unique to different people and different microscopes and different setups. And this ends up creating situations where code is not as well tested as it should be, and it's just not as reusable. So there's a lot of reinventing the wheel, even within our lab. And it's also, we would like to make these analyses perform very quickly so we can do them in real time for these kind of smart scope capabilities. So we want to be able to take an image as it comes off the microscope, analyze it, do the machine learning, extract the information that we need, and then make any changes that like on the fly. And currently we have a lot of spaghetti code that tracks metadata over time, and this is quite a pain. And I don't really think that it needs to be the case. So I'm going to pitch you all on Julia, and specifically the Julia Images ecosystem. It's basically tailor-made for technical computing. The batteries are included, as they like to say. So what's this mean? So the language, in my experience, it's very high level, it's very fast, but the key advantages are that it's composable and flexible. It's easy to write code that is modular and easy to maintain and to test it and reuse it. And I think this makes it very well suited for image analysis, especially now that it's stable. So for those of you who don't know, Julia hit 1.0 close to about a year ago, which is a really exciting milestone. You're on 1.2 now. But this means that your code won't break the next week, which is a huge advantage. It wasn't always true. And so the key kind of ecosystem that I'll be talking about today is the Julia Images ecosystem. But it's really just some extra special sauce on top of base Julia. Base Julia already has a lot of the facilities that you need to work with multidimensional data. So I'm actually going to be showing you guys some code just to give a flavor for what this looks like. So a lot of the microscopy images that we get are in the form of an OME TIFF file. And so the nice thing is that in the background, if you use the standard Julia like file importer, it already knows what OME TIFF files are. So you can just open up, like load an image, and it already loads kind of a lot of information in here. You can probably see this already. So this is using my package behind the scenes, but you don't really need to know that. And basically what you already get out is that, okay, so this image has a y-axis, an x-axis, a time axis, a position axis. Okay, that's cool. The positions have their names, whatever you assign while imaging on the microscope. The time actually has the exact time steps when everything was taken. X and Y already has the spatial information encoded in them, which is like useful. I'll show you why it's cool in a second. And there's a lot more stuff, like if you write any description files in Micromanager and stuff, that all shows up here too. So you can do kind of Python-esque indexing, like NumPy-like indexing, where Julia is one-based index. So if you want to get the first, so we remember it's YXTP. So you can say, like, if we want the first time point and the first position, you can operate on it like it's a standard array, and you get a nice little image printed out, which is the first time slice. But we can also use that metadata to index, right? And so in this case, what I'm saying is that give me the first time point along the time axis, the first slice along the time axis, the first position along the first slice in the position axis as well, and we get the same result. And the key difference here is that this is general. So it doesn't matter what order the axes are in, what their different properties are. This will always work, which is nice. But we have all this extra information. Can we get fancier? So we can also do things like grab the 50 micron window around something, like say the 100th Y pixel. And you can say like from negative 25 microns to 25 microns. It knows what that is and can do this slice behind the scenes, and you get this nice little strip in the y-axis. And this is a view, so this is basically zero allocation, which I'll show in a second. Yeah, and just to show you, it updates all the metadata as you go. So here in this case, now the metadata shows you that it's going from negative 21 microns to positive 21 microns for the y-axis. We can do the same thing on the time axis, where here I can just say, here I'm calling, give me all the time points between 10 seconds and 20 seconds, and it like updates you and gives you a subset of the whole image, where now it's only showing you that section. And so if you want to look at you don't really care about what frame something happened at. It's like when did you add a drug, or when did something key thing happen, and you can look at that specifically, and this will work no matter what the timing is of the imaging. And the fun thing is that this indexing is basically free. So if you actually benchmark the speed of taking this view, it runs in 30 nanoseconds, which is cool, but it's basically only 3 allocations to do the standard indexing. And now if you do the same thing using this general algorithm, it's 60 nanoseconds to run, but again, there's only 4 allocations to do this, which is really nice because you can use these at the bottom of a triple for loop, and it's fast enough to actually use this in an algorithm. And that algorithm is now general. It doesn't care about the storage order. Now, giving you another example of where this is an advantage is, say that we want to compute the mean intensity along the time axis, for example, but images may or may not have a time axis. Okay, so what you can do is basically create what are called traits that you can assign functions with these traits, so that these functions only get run if an image has a certain trait. So in this case, I'm just going to highlight here. There's this nice little trait called has time axis. This is extremely simple. You can define your own of these. But in this case, we want this function to run on all images. So in this case, an axis array, which is an image with all these axes. If it says has no time axis, we're just going to compute the mean of the image. That's straightforward. There's no time, so we'll just get a single slice and we compute the mean of that. But if there is a time axis, what we can do is now iterate over all those time points and compute the mean along that time point. And the fun thing about this is that this is done when the function is dispatched. So when you actually just-in-time compile this function, like the first time you run it, the compiler knows that which function to call based on whether the time axis is present or not. So this is basically instantaneous. And there's no, you can have as many of these as you want, and there's basically no penalty. And just to give you an example of that, so here we're running this mean intensity function that we just defined, and we ran it on our original image that has the time axis. So we get the mean intensities along the time axis. But now we can take a slice of that image and just grab the first time point. And so now there are only x and y axes. And now if we run the mean intensity function, it works again, even though this image has no time axis, because now it's calling the other function that was defined if the time axis is missing. Now the other advantage is that we can do these operations really quickly, especially on like out-of-core data sets. So I think Dask was brought up earlier, but here's a comparison for something similar in Julia, where say if you're working on like a 10 terabyte image, and let's say we want to do a simple transformation, like map a color scheme to this image. Like here we're mapping the magma color scheme to an image. And so there's two different ways of doing this. You can do this eagerly or lazily. And so in the lazy way of doing this is essentially we make a new type. We wrap the data type with a promise that will do something when you actually request the data. We don't actually run it. Okay? And we're going to compare that to actually eagerly evaluating it, where we actually apply it to every single position in this data set. So here all we're doing is applying this color scheme to every single pixel in this image. So naturally, if you do it eagerly, well, it has to go and touch every single pixel in your image. It takes about 500 milliseconds. Great. But the nice thing is that if you do it in the lazy manner, it only has 11 allocations. It basically runs instantaneously, and it doesn't. And this value is constant. So this is big O of 1 essentially. So you can apply it to a 10 terabyte data set instantaneous, and this works for arbitrary functions, like any function that you can write. And the nice thing is that when you view the images, they look identical. It's kind of blown out here, but these images are identical. So this is comparing the output of these two ways of doing this. And the fun thing is this mapped array function isn't doing anything magic. The definition, like the entire package of mapped array, is about 200 lines, and the important stuff is only like 4 lines. So it's incredibly simple in the back end. What it is really, like here I'm applying the log function, which is a built-in, but it doesn't matter. It could be your own personal function, onto a 10 by 10 matrix. And really all it's doing is wrapping up your data in a type that stores the function that you want to apply and a pointer to your data, and just applies that function when you request that data. So it's incredibly simple. And so you could write your own mapped array function or package really easily. So in summary, I hope that I showed you all that the Julia imaging ecosystem is burgeoning with lots of useful features already for image analysis. It's really a joy to develop on top of. I think the fundamentals are very powerful, but it definitely needs a lot more development to compete with the extensiveness of other ecosystems. And finally, I want to thank Dr. Tim Holy at the University of Washington University in St. Louis. He created the Julia imaging ecosystem, my lab, and funding. And I'm on GitHub, and including some of the packages that were mentioned here, and love to see activity, pull requests, all that. So thank you so much for having me, and yeah, that's all.
I'll ask a question. So there's an enormous amount of effort that's been put into developing image processing algorithms in other languages. Mm-hmm. And I guess what we're seeing now here is things are being built from scratch again. But yep. The interaction story between Julia and Python is quite good, right? So
it is.
Do you have any thoughts or comments on that?
Yeah, I actually use that every day. I haven't done it from the other direction, so I haven't called Julia from Python. But calling Python from Julia works extremely well. So I use, there's a package called PyCall, and I use quite a few Python packages, especially the data frame ecosystem seems to work really well, translating between the two. Generally for images, I haven't seen that too commonly used. But I would like to emphasize that a lot of the advantages that come from like the fundamentals here, I think are where Julia's advantages are. Python, definitely the extent of what's available, it's no comparison. But I think that the flexibility and adaptability, and I think going forward, as a developer, it's really nice to work in this environment. But as a user, definitely, it's still early. I hope that answers your question.
Any more questions? Raise your hand.
I'll ask
Don't be
another
shy.
one, perhaps.
Oh, there's a question?
You mentioned out of core.
Yeah.
So Dask, for example, allows us to like spread things, you know, on different cores on a laptop or on different nodes in the network. What's the story there for Julia in terms of utilizing clusters and that sort of thing?
So it actually, there's a Dask-like package called Dagger, which does the same thing. I haven't personally used it myself, but it does has a lot of Dask-like features, and you can spread it across an entire, like spread computations across an entire supercomputer. They use it for like extremely fast computations. I think the key advantage, I would say, is that the ease of writing flexible and like maintainable code is where the advantage is for using Julia. And I think it's really easy to write your own packages. It's really easy to distribute them. It's really easy to test them, make sure they're reliable. So I think that even though the packages are very new, in general, I find them to be quite high quality and quite reliable. But you know, there is some reinventing of the wheel here. All right, thank you all. Yeah.
Sort of curious to deal with pictures. I mean, we had a tutorial here using scikit image, so you go from the image representation, and you talk a little bit about that up to a series of different transformations using sort of more classical image processing, like edge detections, mathematical morphology. Is it the case that you also have all these capabilities as part of Julia for image processing? What's the stage?
Yeah, so certainly there's a lot of the basic stuff. So yeah, basic edge detection, Gaussian blur, like for example, like blurring, like Gaussian blurring, like arbitrary kernels to your images is extremely fast in Julia.
Segmentation methods as well?
Segmentation, there's like all the basic ones. I mean, you know, watershed, compact watershed, like the various derivatives. So all that stuff is built out. There's definitely, it's not as comprehensive, but I would say all the major stuff is there. And so I've definitely been able to do all of my cell segmentation, everything really, really well with the Julia ecosystem. But there's definitely some of the edge cases where like MATLAB or Python have more available.
That's very exciting. So the place to take a look at some of the scripts using Julia for some of these classical image transformations are available in your repository?
So I don't have examples of that, but I have links to the Julia Images documentation, which has like, it's very thorough documentation. And so they're like examples, and they have like, you know, taking through like the guy looking through the camera, like the standard images, and examples of segmenting and everything through that. So there's the documentation and the testing and stuff is quite good already. And so a lot of that stuff is there. But I would say that still there's some of the edge cases aren't well handled. But I think there's already some places that it stands out where I think like the speed of a lot of the calculations is very good. For example, I think there was a benchmarking of Julia's ability to convolve kernels like arbitrary kernels versus Fortran and C, and it beats everything by a lot.
Wow.
And so the ability to write extremely fast code that's readable and usable, I think is where the advantage is. And I think that as a developer, like, you know, I think you appreciate that. And then I think if more and more developers realize at the ease of maintaining these packages, that's where the advantage will come. But that's to be seen if that's going to turn out to be the case.
Awesome. Thank you so much, Tamas.
Yeah. Thank you so much.